For more than a century, general relativity has been our map of the cosmos. It's guided us, it's made incredible predictions, but what if it's just that, a map? An unbelievably accurate map for sure, but not the actual territory itself. What if Einstein's beautiful, famous equations aren't a fundamental law of nature, but something that emerges from a deeper, more fundamental reality? Today, we're diving deep into a scientific paper that makes a really compelling case for exactly that. It proposes a whole new way to derive gravity itself. And here it is, the heart of general relativity, the Einstein field equation. On the left side, you've got g mu nu, the Einstein tensor. That's basically the geometry of the universe, the literal curvature of spacetime. And on the right, T mu nu, the stress energy tensor. That's all the stuff in the universe, all the matter and energy. Now, this equation has been just phenomenally successful, no question. But it leaves this huge, profound question just hanging in the air. How? How does matter actually tell spacetime to curve? Is it just a fundamental rule with no explanation? Or is there a physical mechanism, something actually happening, that this equation is just describing the results of? That's the big question we are tackling. So, here's our game plan. We're going to break this journey down into 6 parts. First, we'll look at the conceptual gaps in Einstein's incredible story. Then we're going to introduce a radical new idea, a living vacuum. From there, we'll check out the universe's rulebook according to this new theory. And then, this is the big one, we'll actually derive gravity from it and see how Einstein's equation just pops out. And finally, we'll step back and really think about what this new map of reality could mean. Okay, let's kick things off with Einstein's unfinished story. And let me be clear, we are not here to poke holes in general relativity. Its triumphs are legendary, they're undeniable. What we're going to do is look at the questions it doesn't answer, the little conceptual cracks that suggest, hey, maybe there's something more going on here. You see, general relativity is a brilliant description of gravity, but it's not really a complete explanation. It tells us that mass and energy curve spacetime, but it doesn't tell us what spacetime is. What is the actual physical stuff that's bending? And how does a change in that curvature, a gravitational wave, actually travel from point A to point B? GR is totally silent on the underlying mechanics, and that silence gets deafening when you bring quantum mechanics into the room. Quantum field theory tells us the vacuum isn't empty at all. It's the simmering pot of virtual particles popping in and out of existence. How on earth do you connect that idea with GR's smooth geometric picture? These are the gaps that this new theory is trying to fill. And that brings us right into our second section, the living vacuum. To even start answering those big questions we just laid out, we need a new way of thinking. And this is where the paper we're looking at introduces a concept called dynamic vacuum field theory, or DVFT for short. This slide really gets to the core of the paradigm shift. On the left, you have the standard picture. Spacetime is like this passive stage, a big rubber sheet that gets bent when you put something heavy on it. But on the right, you see the DVFT idea. The vacuum isn't a stage. It's an active physical medium, almost like a fluid that fills everything. In this new picture, matter doesn't curve some abstract geometry. It creates distortions in a real physical field. Gravity isn't just curvature, it's the pressure and flow of this vacuum field. So how do you actually model this vacuum fluid? Well, the theory proposes this complex scalar field, represented by the equation you see here. Let's break it down. It's not as scary as it looks. The rho symbol, that's the amplitude. You can think of it as the density or the stiffness of the vacuum. A higher rho means the vacuum is stiffer, more energy dense. Then you've got theta, which is the phase. This acts like a little internal clock at every single point in the field, governing how it oscillates and evolves over time. So at every point in space, we have 2 key properties, the vacuum stiffness and its internal rhythm. These are our fundamental building blocks. Now, when it's undisturbed, far away from any matter or energy, the vacuum is perfectly uniform. Its amplitude, that stiffness rho, is constant everywhere, and its phase, theta, just ticks along linearly with time. It's like having a perfectly synchronized set of clocks, one at every point in space, all ticking at the exact same rate. This is the perfectly still, calm surface of the cosmic ocean before we throw any rocks into it. All right, let's move on and see how this all starts to build. Section 3, the universe's rulebook. Pretty much every modern physical theory, from particle physics to cosmology, is built on a single, powerful master blueprint. It's an equation that you can derive everything else from. In physics, we call this the action principle. And this is the action for the entire theory. It's a single quantity that basically contains all the rules for the whole system. The universe, it turns out, is a bit lazy. It always evolves in a way that minimizes this value. That's the principle of least action. So let's look at the ingredients. The R term, that's your standard Einstein-Hilbert action for gravity.
It's the part that describes the dynamics of spacetime geometry. The LM term is the Lagrangian for all matter and all the fields of the standard model. But the new, absolutely crucial piece is that L phi in the middle. That's the Lagrangian for the vacuum field itself. This is the rulebook for how the vacuum behaves. And by putting all three together, we finally have a unified description of geometry, the vacuum, and matter. This is ground zero for everything that follows. And if we were to peek inside that vacuum rulebook, that L phi Lagrangian, we'd find a few key things that give it its character. There's a term for the kinetic energy of the amplitude. That's the energy it costs to squeeze or stretch the vacuum's stiffness. There's a potential energy term, V of rho, which is what gives the vacuum its structure and baseline stiffness to begin with. And finally, there's a kinetic energy term for the phase. And this is what determines how waves and disturbances actually travel through this vacuum medium. Okay, now for the main event. Section 4, Deriving Gravity. We have our master blueprint, the action. So how do we get from that one compact equation to the actual physics of gravity that we see in the universe? We use one of the most powerful and honestly beautiful ideas in all of physics, the principle of least action. The derivation itself follows a pretty standard but powerful procedure in theoretical physics. We start with our action. Then we do something called varying the action with respect to the spacetime metric, g mu nu. This is the math that brings the principle of least action to life. By basically asking, how must spacetime behave to make the action as small as possible? We are, in essence, deriving the law of gravity. This process spits out the field equations that govern the whole dance between spacetime, matter, and our new vacuum field. And here is the result of all that math. On the left, we still have our good old Einstein tensor, describing the curvature of spacetime. But look at the right. That's the source of the curvature. And now there are two sources. We have the familiar stress-energy tensor for matter, T mu nu of m, but now we also have this brand new term, T mu nu of phi. This is the stress energy of the vacuum field itself. The vacuum is no longer a passive backdrop. It's an active participant, an active source of gravity. Let's just be super clear about what this means. T mu nu of phi, that's business as usual. It's the energy and momentum of all the matter and radiation. But T mu nu of phi? That's revolutionary. It represents the energy and momentum of the vacuum itself. The energy stored when it's compressed, the momentum carried by waves rippling through it. This equation is telling us that the vacuum is a dynamic, energetic substance that actively creates gravity, just like a star or a planet does. Okay, this brings us to an absolutely critical point. If this new, more complicated equation is the real deal, then where did Einstein's original equation go? I mean, why does it work so incredibly well? Let's jump to section 5. The Einstein equation emerges. The secret, it turns out, lies in something called the low gradient limit. Let's just ask the question straight up, because this is the key to connecting this new abstract framework back to the physics we've known and trusted for over 100 years. If the true equation of gravity has this extra piece for the vacuum's energy, how in the world did we miss it for so long? And the answer is something called the low gradient limit. This just describes a physical situation where the distortions in our vacuum field are really small and change very slowly over huge distances. Think of long, gentle swells on the ocean, not sharp, choppy waves. It just so happens that the gravitational fields of our sun, of Earth, of all the planets, while strong enough to keep us in orbit, are actually pretty gentle on a cosmic scale. They create exactly these kinds of low gradient disturbances in the vacuum. And here is the punchline. In this low gradient limit, the stress energy from the vacuum field, our new T phi term, becomes vanishingly small compared to the stress energy from regular matter. The vacuum's contribution to gravity is still there, technically, but it's so tiny that you can basically just ignore it. Or it simplifies into a simple constant, which looks exactly like the cosmological constant in Einstein's original setup. Either way, for all practical purposes, it disappears from the equation. And this slide just perfectly illustrates the big reveal. On the left, there's the full, fundamental equation from dynamic vacuum field theory. On the right, you see what happens when you look at it in the low gradient limit. The physics of our solar system, our cosmic neighborhood. That T phi term just fades away, and we're left with g mu nu is approximately equal to 8 pi g times T mu nu of matter. Boom. We get Einstein's original field equation back. Perfectly. So the takeaway here is profound. Within this new framework, general relativity isn't the fundamental law of gravity anymore. Instead, it emerges as an incredibly accurate, incredibly successful, effective theory.
It's a theory that works perfectly under the specific conditions where we've been able to test it most precisely, but the true underlying theory is richer, deeper, and includes the dynamics of the vacuum itself.
Now, reframing our most successful theory of gravity like this, well, it has some absolutely massive implications for physics. So let's head into our final section to unpack them. Section 6, a new map of reality. What does it all mean for our understanding of the universe if this is really how gravity works? So why does all this matter? Well, first, it finally gives us a physical mechanism for gravity. It's not just geometry, it's the physics of a field. Second, by treating the vacuum as a quantum field, it offers a potential bridge to quantum mechanics. But here's where it gets really exciting. It might just offer a solution to the whole dark matter mystery. See, on the scale of an entire galaxy, the gravitational gradients are way bigger, and the vacuum's response could become nonlinear. This could create a kind of effective gravity that mimics what we attribute to dark matter, explaining why galaxies spin too fast without needing to invent some new, mysterious particle. It's a huge deal. And finally, it takes a real step toward a unified theory by putting geometry, the vacuum, and matter all on the same team. We'll end with this one final provocative thought. For centuries, we've thought of the vacuum as the very definition of nothing, emptiness. But theories like this one suggest it might be the most complex and fundamental thing in the entire universe. So if gravity, the force that builds stars and holds galaxies together, is just a ripple, an emergent property of this cosmic medium, what other phenomena, what other secrets, what other kinds of physics might be hiding in plain sight in the apparent emptiness of space?